Magnetic fields, like we already discussed, these fields does not exist in reality. And Einstein, for the first time, proved that. They are again electric fields, some forms of the electric field. When the electron moves, uh, their electric field, the electron's electric field, relative to the positive proton electric field. The proton is normally very static inside the metal or inside the conductor. So when the electron moves in the conductor, the moving electron's electric field relative to the static proton's electric field, right? Plus the external applied electric field makes a relative electric field, a very disturbed pattern of the electric field. That different pattern of the electric field is known as the magnetic field for the world, right? And for centuries, they call this as the magnetic field. However, in reality, it does not exist. So magnetism, the concept of magnetism is way back historically from the era of the Babylonians. Um, Chinese, for the first time in the 11th century, developed compasses based on these magnetic field. But remember, in reality, these field does not exist. They are again the electric fields. Okay, some form of the electric field. So, but this different, very different forms of the electric field is known as the magnetic field for the people, for the people of the world, right? But Einstein is not agreed with that. Okay. Anyway, so Chinese for the first time developed those compasses based on the magnetic fields in the 11th century, which was giving you the direction of the north of Canada, right? So the compass, the north of the compass moves to the north of the Canada, right? Which is actually the south of the planet Earth, right? So these fields are very useful. The concept of the now the Earth's magnetic field is coming from huge molten iron, which is there inside the innermost core of the Earth, and that molten iron is moving. So, as per Einstein statement, when the charges or ions they move, the electric fields of these moving ions or charges in relativity to the static charges produce disturbed patterns of the electric field, and those patterns are called as the magnetic field. So that the movement of that huge molten iron inside the innermost core of the earth is causing the magnetic field of the planet earth, right? And it's very good. This magnetic field is very useful, and it protects us from many electromagnetic phenomena coming from the sky or from the upper atmosphere. So this magnetic field is important for the integrity of the of our Earth, right? So we will have some good time on the concept of this magnetic field, but typically these magnetic fields are coming from the movement of the electrons. So suppose if I take the hydrogen atom, one hydrogen atom. Uh, the electron in the hydrogen atom revolves with tremendous speed as per the Bohr's model. Uh, so this electron is moving with tremendous speed. Okay, and if I use my right hand, uh, if my fingers shows the curls, if my finger shows the curls of movement of these electrons, the path of these moving electrons, if my curls, so then my thumb will give you the magnetic moment of this atom. So since in this hydrogen atom, there's one electron and that electron moves with tremendous speed. So hydrogen atom itself is a very, very powerful magnet. But as we said previously, The problem with the hydrogen atom that it does not exist in the atomic form, and it will always make a bond. It will always make a bond with another hydrogen atom. Okay, so the two will always make a bond but it will always make a bond when the orientation of the electrons or the electron cloud or the movement of the electrons in the second hydrogen is just opposite to the movement of the electron in the first hydrogen atom. So when the magnetic moment precisely are opposite to each other, for example, in hydrogen, this movement of electron is anti-clockwise, and in this one it's clockwise. So the two movements are precisely opposite to each other. Now, now the two hydrogen atoms will quickly combine together to make a hydrogen molecule, and the magnetic moment of the two hydrogen atoms will cancel each other. So, by definition, every atom is a magnet, but their molecule may not be atoms, right? So, based on these definitions, all the materials in this universe are classified into five categories. Uh, the paramagnetic, the diamagnetic, the paramagnetic, the ferromagnetic, the ferrimagnetics, and the antiferromagnetic materials. And based on the orientation of the moving charges inside these materials, will classify them in different categories. Like they would behave like a diamagnetic or paramagnetic or ferromagnetic or ferrimagnetic or antiferromagnetic materials. So by definition, every atom is a magnet, but it's really how a chunk of atoms or molecules or their electrons they move, and will they cancel the movement of each other or not, will make certain material powerful, some materials less powerful magnets, some very neutral, right? So magnetism is there because of the movement of charges, no matter if it's a natural magnetic material. The magnetism of the magnetic material still is coming from the movement of these electrons inside their structures, right? And again, you can make your magnetism if if you move the electrons inside a conductor. If you move the electron inside a conductor opposite to the electric field. If the electron moves opposite to the electric field, it will again make a magnetism, right? It will again create magnetism. So when you remove the electricity or the battery from the conductor, the magnetism will no longer exist. So, so you can have many ways of producing this magnetism, right? But there's some basic theory. Theory is there are no magnetic point charges, no magnetic point charges. Just like with electric charges, we always have positive, negative, right? We always have positive and negative, and the two combine together to produce the charges, and there's a Coulombic force of attraction or repulsion between them, and that's also causing the electric field intensity to exist. That also means the electric energy. So for electric field, there is a point charge, but there is no point charge for the magnetic field. Remember, the source of the electric field is a charge. There is no source for the magnetic field. Remember, it's since, as I said many times, and it's the argument of the uh, Einstein also, the source of the magnetic field is relativity of a moving charge in reference to a static charge. Okay, the source of magnetism is relativity. Relativity of relativity of electric field of moving charge with respect to a static charge. That will create the magnetism. that will create a disturbed pattern for the electric field, which is called as the magnetism. So by definition, if we generically look at this situation, for the electric field, the source is the electric charge. See, always if we have the positive field, positive charge, we have the electric field which is going out. If we have the negative charge, it's the electric field which is coming in, just by convention. Okay, so the source of electric field is always charged, but there's no no magnetic charge in this universe. Again, it's the moving. If you move this negative electron with respect to the static positive, you end up on magnetism. So you can say the source of the magnetic field is a moving charge. That's true, but itself there's no governing body which produces this magnetic field. Okay, so Einstein was right. It's only the electric. It's again the electric. The magnetic field is again the electric field, some form of the electric field. Okay, so by definition, there are no magnetic point charges. There are point charges for the electric field, but there are no point charges for the magnetic field. Okay, so for example, if I have this magnet, north and south, so if I break this into half and I collect only the south, again I will end up on the north and south. Okay, again I will end up on the north and south. If I further make this half, again I will end up on the north and south. Okay, so so I will always get two poles, right? Just opposite to the electric field where we have a monopole, a monocharge. In the magnetic field's case, we always have a dipole. Okay, we have two poles always. So we always have the south pole and the north pole. Uh, there's another theory: if there's no permanent magnetic present, if there's no permanent magnetism. By permanent magnetism, what we mean? The permanent magnetism is caused by electrons spins in atoms or material. So the natural spin of the electron, just like here in the hydrogen case, okay, the natural spin of the electron in the hydrogen case or in any atom or in any material is causing the permanent magnetism. Okay, but look, whenever the two hydrogen atoms combine together, the magnetism is gone. Okay, so it's not a permanent magnet. Hydrogen molecule is not a permanent magnet. However, hydrogen atom is a very, very good magnet, but the problem with the atom is it do not like to stay in the atomic form. It will always make a molecule, hydrogen gas, H2. H2. The two hydrogens combine together to make the hydrogen gas, right? So there's a theory. If there's no current flowing in a circuit, there's no magnetic field. Okay. If look, if there's no permanent magnetism, if there's no permanent magnetism, and if there's no current, that means there's no magnetic field. So if the material is not perfect, yes, yes,
सर
yes,
बात नहीं
yes,
सर
yes.
ये परमानेंट मैग्नेटिज्म कौन सी होती है सर
हाँ, परमानेंट मैग्नेटिज्म मैंने आपको बताया ना कि फॉर एग्जाम्पल अगर आप समहाउ हाइड्रोजन एटम को मॉलिक्यूल बनने से रोक ले, तो हाइड्रोजन एटम्स अगर सारे के सारे हाइड्रोजन एटम्स आपके पास पड़े तो दे विल प्रोड्यूस very very strong magnetism. Okay, there are materials called as ferromagnetic materials. Ye materials, they can give you the permanent magnetism. Okay, so why? Because in the ferromagnetic materials there are domains. If suppose this is a ferromagnetic material, okay, so there are domains. And why we call them domain? Because one domain is a set of atoms or molecules. One domain is a set of atoms or molecule, maybe thousands, maybe a million set of molecules or atoms. Now, just like if you take the hydrogen atom, the electron will move in one specific direction, for example, counterclockwise, right? So if in one domain, all the electron spins are in one direction, and suppose they produce magnetic moment in this direction, but there might be another domain here, which will have very opposite magnetic, which will have very opposite electronic spin in the atoms or in the structure. So the magnetic moment of this blue domain will cancel the magnetic domain of this green domain, right? So, but for a permanent magnet, the green spins will be very large in comparison to the blue spins. Okay, so there will be many green domains, many green domains in comparisons to the blue domains. So effectively that material will show you some permanent magnetism. That means it will always behave like a magnet. Okay. However, there will be some red domains which will have a very opposite, a very different electronic spin. There might be very few. There might be very few orange domains. Very few, right? Very few orange domains. There might be very few yellow domains. There might be very few yellow domains. It's like this one. There might be very few black domains, for example. Okay, but if you have one kind of magnetic if the magnetic spin of one kind is predominant in the entire structure, that structure is going to show you a permanent magnetism. Remember, by this arrow I mean the magnetic moment. What is the magnetic moment? Uh, what is the magnetic moment? Magnetic moment, if, for example, if I turn on my camera, the magnetic moment is, the electrons are spinning in the direction of my fingers, right? So the thumb is going to give us the magnetic moment, okay? If the electrons are spinning in the direction of my fingers, thumb is going to give us the magnet. So that's the net magnetic. That's the net magnetism which is going to happen in the direction of the thumb. So by these arrows, I mean the magnetic moment. So if in one domain there's a huge number of electrons or molecules within those atoms, or inside the molecule, if the electron spin is in same direction, they will produce magnetic moment in one direction. Say that's the green one. And probably there's another green domain, there's another green domain, there's another green domain, and there are many green domains, right? Now, such materials, there's one more characteristics of such materials. If if you apply some external magnetic field to them, if you apply some external magnetic field to them, some external magnetic field to them, then what happens? Then what happens? Then most of the domain will reorient themselves in the direction of the external magnetic field. If I apply the external magnetic field, this this red domain will quickly align itself in the external black magnetic field. If I apply see, this blue domain will quickly reorient itself in the direction of the external magnetic field. This green domain will quickly reorient itself in the direction of the external magnetic field. It means it's a very good material. showing some excellent magnetism. Okay, so based on these few characteristics, one is the domain, the other one is response to the external magnetic field. If the electronic spins in the domains, they reorient themselves and produce such a magnetic moment which aligns itself to the external magnetic field. Such materials are very, very powerful magnets. Okay, so they have two characteristics. One is uh, in the absence of external magnetic field, they show they have predominantly more domains in which electronic spin is in same direction. So they present permanent magnetism. Their second characteristic is that if external magnetic field is applied to them, they reorient their domains and they align themselves to the external magnetic field. That's the two characteristics they have. However, there are some materials when you apply the external magnetic field, the black magnetic field from right to left, they reorient themselves against their external magnetic field. So their domains reorient themselves against the external magnetic field. Effectively, they are trying to cancel the external magnetic field. So such materials, they show very weak magnetism. Okay. So based on these characteristics, all materials in this universe are classified into five categories: the diamagnetic, the paramagnetic, the ferromagnetic, the ferrimagnetic, and the antiferromagnetic. And we'll have some discussion on these five classes of magnetic materials probably in the next class. Any question to this point? Any question here?
No, sir.
Okay, so if there's current flow, there's always magnetic field produced. Remember, if current is flowing through, remember current will flow through metals or through conductors. There will always be a magnetic field there. Okay, so see, so in the absence of permanent magnetism, which means the material is not having the domains, the material doesn't have those domains, uh, material doesn't have those domains, then in the absence of, remember all these green, they will reorient themselves in the direction of the external. So if there's no permanent magnetism there, there will be no, and if there's no current, there will be no magnetism. If there's a current, there will be magnetism. Okay, so what's the origin of the magnetic field? Uh, it's again the spin of the electron inside the atom or flow of the electron inside the metal. Okay, remember, if you have the atom, the electron, as per Bohr's model, is spinning around the nucleus with tremendous speed, with very, very high speeds. Okay, it's in the range of 10 to the power 6 meter per second. Very, very high speed of this electron spin. But as we saw one example in chapter number 5, when you apply some voltage potential difference to a conductor, right? There will be electric field in the conductor, and the free electrons will move against this electric field, and the speed of that free electron is very, very low, like it was 5 meters per second when the current was, when I was 27 ampere. Okay, it's very low speed, extremely low speed. However, when the electron is in the atom, it has a tremendous speed of 10 to the power 6 meters per second. It's a huge speed. Okay, so depending on the current, if you raise the current, if I is raised, this electron speed will also raise. Okay, if and that will occur if you raise the voltage. If you raise the voltage, current will raise and the electron speed will raise. So these are the few theories which we have already and discussed. Okay, so two parallel DC current carrying wires. Say we have wire number one, okay, and then we have wire number two, and say DC current is flowing through it, uh, and say the current I is in the same direction. Current I in both the wires is in same direction. Uh, they will have an attractive force. They will have an attractive force. Okay, so the two wires will attract each other if the direction of the current is same. If the direction of the current is opposite, they will repel each other. Okay, this is not due to Coulombic attraction. A sheet of floating metal placed between the wire has no effect. So if I bring a metal sheet here between those two conductors, if I place a metal sheet, this will not affect the force of attraction between those two conductors. So metal sheet is not going to affect the magnetic field. Okay. Uh, a sheet of floating metal placed between the wires, floating, remember, has no effect on the force. Okay. So it has no effect on the force. Okay. The magnitude of the force between the wires is proportional to the current I1 and I2. So this force is proportional to current I1 and I2, the product of the two. Okay. And is inversely proportional to the square of the distance between them. Okay. So if we have the distance between them is say R, so then this force is inversely proportional to the square of the distance. Okay. If the direction of the current flow are opposite, the force will be repulsive. Okay. Magnetic fields cannot be experienced solely on the basis of Coulomb's law, but when combined with special relativity of Einstein, special theory of relativity, okay, the existence of a field that is related to moving charges appear. And I guess we have already made some talk on this. That was probably chapter number 5. In chapter number 5, we discussed this phenomena. In chapter 5, if you remember, I draw a few diagrams in those lectures. Okay. There's a magnetic force, always will be. The force is already known to you. That force will be proportional to the cross product of the velocity of the charge and the magnetic field. Okay. So if the electron is moving in this direction, if the external magnetic field is in this direction, the force will be perpendicular to the two. Okay. So there will be a force which is the, say, velocity is in x direction, magnetic field is in y direction, this will go in the z direction. Okay. This will be z direction, so perpendicular. Okay. So if this is if the electron is moving with velocity, remember, if this is the conductor, okay, if the electron is moving in this direction, it's only possible that you have an electric field over there. Without the electric field, this electron is not going to move. You have an electric field in this direction, only then the electron will move. And if you apply an external magnetic field, if you apply an external magnetic field, suppose in this direction, okay, so say this is B. So B, so the velocity, the velocity is in this direction. B is perpendicular to it. So V cross B into electron will make the force. So force will be perpendicular to it. So if this B is in X direction, velocity is in Y direction, so you have the force. Suppose for simplicity, I make this Y direction, this one as the X direction. So force will be in the Z direction. Okay. because x cross y, x unit vector x cross unit vector y is going to make unit vector z. Okay. So if current is flowing through a wire, you can find the magnetic field using your right hand. You can through a solid through a loop of wire, if the current is flowing through this, you can again the magnetic field is going to you can again take advantage from your right hand, and you can find the direction of the. Remember these these magnetic lines of forces, they will always make loop. So this loop will somehow come back and will end up here. Okay. So these magnetic lines of forces, they always make loops. They make a complete. Electric lines of forces were straight lines. Magnetic lines of forces, they will always make loops, closed paths. Okay. Because remember, magnetism will always come when the electron moves. When the electron moves, you have kinetic energy involved there. So when you have kinetic energy involved there, you end up on a potential difference. And if it makes a complete round trip, you come back to the same point. The potential difference makes a closed loop, which goes to zero. So the work done is involved. Okay. So for this purpose to exist, for conservative electric field, for the law to exist, these magnetic lines of forces, they have to make complete loops, otherwise they will not exist. Okay. So so see, here we are connecting many things from our previous discussions which we saw in previous chapters. We are connecting them. Okay, this is a magnetic field of a permanent magnet. Here see the magnetic field of the earth. An example here about the Hall's effect. The Hall's effect is just like I draw this this example here. This one. It's very much the explaining the Hall's effect. Let's see Hall effect in a different way, slightly different way. Okay, suppose this electron is moving to the right. It will only move if the electric field is in to the left. Electron is moving to the the electron is moving to the left. It is moving to the left in a specific direction because that the electric field is towards the right, and say the magnetic field is upward. Magnetic field is upward. Okay, so the magnetic field, this one is the electric field. Okay, so then see, the B field is in this direction. The velocity is in minus x direction. Okay, and you have this force. The force will be in this direction. Okay, say minus y here. Okay, this one is y. If this is y axis, so this the other side of this is minus y axis. This is x axis. The other side of this is minus x axis. The B field is in z direction. So see, by the cross product, we have F equals to uh, electron dot V cross B. Remember, there are two types of forces on this electron. There's another force on this electron. There's another force on this electron. That force is electron charge into electric field. Okay, QE, electron charge. Okay, QE. Okay, so there are two forces. So combine these two forces. The total force on this electron will be F magnetic and F electric. So F magnetic plus F electric. So there are two forces. Total force is the sum of the two. Why we simply add them together? We do not simply add them together. We add them in the vector domain. But why we can add the two forces? Because it's very easy, very simple. The magnetic field is again the electric field of some form, of some kind. So you can straight away add them together. But why you add them together? Because it's always in the space. The relativity of the electric field is always in space, not in time. Okay, the relativity of the electric field of a static charge with the moving charge is always the space phenomena. So you add them together. Okay, so you add the two forces, and when you do that, the total force is called as the Lorentz force. Okay, so sometime in some books, only the magnetic force is called as Lorentz force. Okay, so you will find in some books only the magnetic force has the Lorentz force, but in some books, like in this text of the William Hath, you will find the sum of both the forces as the Lorentz force. Okay, so see, when you combine these two forces together, which is QeV cross B plus QE into electric field. So that means you can make a constant QE here. It would be V cross B plus all our vectors. Okay, and then you can use your algebra of XYZ and those kind of things. X, Y, and Z. So you can use your space coordinates algebra, the geometry, to find out the direction of the force. So I guess that will be too easy for you. See an example here of the Lorentz force and the Hall's effect. The magnetic field is in this direction. The electric field is in this direction. The electron is moving in this direction. So the velocity is in this direction. So see, velocity of the electron cross B. If the velocity is in X direction, actually minus X direction. Velocity of the electron is in minus X direction. B is in Z direction. So force is going to be in Y direction, but in negative Y direction. Okay. So the electron is moving in minus X direction. So force will be minus Y direction. This is the force. This is the velocity. And this one is B. So B, the magnetic field is in upward direction, is in the plus Z direction. The velocity of the electron is in minus X direction. This is the velocity. And the force will be in minus Y direction. Okay. So this will be plus X and this will be plus Y. So here you can make your calculations. So you use the concepts of your calculus and analytical geometry, right? Any question here? Any question here?
सर इसमें हमारे पास जो मैग्नेटिक फील्ड है उसकी जो डायरेक्शन होती है वो कैसे पता चलती है हमें
मैग्नेटिक फील्ड की
अपवर्ड है या डाउनवर्ड है
अच्छा राइट ओके एक मिनट इसकी डायरेक्शन हमें कैसे पता चलेगी
यस सर तो क्योंकि हमें वेलोसिटी की तो पता चल जाती है ना कि वो जैसे हम इलेक्ट्रिक फील्ड अप्लाई करते हैं तो उसके ऑपोजिट डायरेक्शन में हमारी वेलोसिटी आती है
हाँ हाँ सही सही कह रहे
हम मैग्नेटिक फील्ड का कैसे कह सकते हैं
for example we have a permanent magnet here, okay, and say this is the south pole and say this one is the north pole, right? So the field will move from north to south, right? See, always the case of motors, you have poles, right? You place the poles, the north and the south pole, and the north is the combination of them, right? and then you rotate the coil in that poles, right? Remember that. So the biggest application of this magnetic force is in the machines where you place your poles. अब ठीक है, क्लियर है?
अच्छा सर, एक और क्वेश्चन है
जी जी
सर। मैग्नेटिक फील्ड और इलेक्ट्रिक फील्ड सर आपस में सर परपेंडिकुलर है, सो सर ये ऐड किस तरह हो रही है?
आपस में परपेंडिकुलर है, ठीक है। देखो, अगर परपेंडिकुलर है तो ऐड हो सकते हैं, राइट? ठीक है। देखो, इलेक्ट्रिक फील्ड्स का, आई गेस यू मीन टू से दैट the electric force is in this direction, right? You mean to say that the electric force is in this direction, यही कहना चाह रहे हो ना?
यस सर।
तो इलेक्ट्रिक फोर्स और मैग्नेटिक फोर्स आपस में लॉरेंट्स इक्वेशन से हमेशा एक दूसरे के क्या आने, परपेंडिकुलर आने। ओके,
सही
सही है। दिस फोर्स इज लॉरेंट्स, as I said in some books it's called as Lorentz force. Okay, only the magnetic force sometimes is called as Lorentz force, but as I said, the sum of the electric force and the magnetic force, the two are called as the Lorentz force. Okay, समझ आ रही है बात की?
यस
या अच्छा, आपका क्वेश्चन is going to take me to a new thing, right? Because look, probably आप ये कहना चाह रहे हैं कि हमारे पास सपोज ये कंडक्टर है, okay, this is a conductor, right? So if I connect this through a battery, okay, I have this positive, this negative, I will end up on this electric field which is going in this direction, right? Okay,
यस
अब बिल्कुल ये कहना चाह रहे हैं। अब हमने क्या किया है कि हमने एक परमानेंट मैग्नेट लिया है, whose south pole is here and the north pole is here, okay, which is basically causing a magnetic field, which is causing a magnetic field moving from the south, ending on the which is moving from the south north and ending on the south. Here is the magnetic field. तो आपके कहने का मतलब ये है कि ये जो फोर्स है ये वाला जो
हाउ डू दे ऐड अप सर? यस,
how they add up together. अच्छा, the answer is कि इनका add up होना इतना इश्यू नहीं है, ये add up easily हो जाते, okay, because they are the forces. लेकिन probably या तो आपके जहन में है या नहीं है, या आपका सिक्स सेंस इसको कहीं और लेके जा रहा है। Wait, I have a little problem with connectivity. इसको थोड़ा सा मैं इसको दोबारा कर लेता हूँ। This is our electric field. Okay. Also, I have electric force here in this direction. Okay. And the magnetic field was in this direction, and I end up on a Lorentz force which was in this direction. Okay. As per all these calculations, in the Lorentz force, this is in minus y direction. F, this was in x direction. Okay. Or this was in z direction, right? Okay. अच्छा, देखो, probably आपका क्वेश्चन ये है कि ये मैग्नेटिक फोर्स, अगर फॉर एग्जांपल मैं बैटरी रिमूव कर देता हूँ, ओके, एक मिनट, अगर मैं बैटरी रिमूव करूं, बैटरी रिमूव हो गई है, तो कौन सी चीज खत्म हो जानी है?
इलेक्ट्रिक फील्ड।
इलेक्ट्रिक फील्ड खत्म होना है। अब देखिए, इलेक्ट्रिक फील्ड खत्म हो गया, राइट? अब हमारे पास फ्री चार्ज है ना, ये फ्री चार्ज, ये इलेक्ट्रॉन है ना, अभी भी है, बट क्या ये इलेक्ट्रॉन अब मूव कर सकता है ऐसे?
नो सर,
कभी भी नहीं
सर नहीं
करेगा।
करेगा।
हाँ, एग्जैक्टली। Why? Because look, we have this equation. The force is the total force is the electric force plus the magnetic force, right? अगर हम कहें कि इलेक्ट्रिक फोर्स क्या है, जीरो है, सो एफ मैग्नेटिक कितना है, इट्स क्यू ई वी क्रॉस बी,
बी।
ऐसा ही है। अच्छा, अब देखो इलेक्ट्रॉन में वेलोसिटी किसने लानी है, इलेक्ट्रॉन में
इलेक्ट्रिक फील्ड
इलेक्ट्रिक फील्ड।
इलेक्ट्रिक फील्ड ने लेके आनी है। तो इलेक्ट्रिक फील्ड इलेक्ट्रॉन में वेलोसिटी लाएगा तो मैग्नेटिक फोर्स प्रोड्यूस होगा। रिमेंबर, फ्री इलेक्ट्रॉन पे अगर अगर वेलोसिटी जीरो है, मैग्नेटिक फोर्स स्ट्रेट अवे जीरो हो गया। इन द एब्सेंस ऑफ इलेक्ट्रिक फील्ड, मैग्नेटिक फोर्स तो चार्ज पे कुछ कर ही नहीं सकता। दिस ऑल्सो मीन्स मैग्नेटिक फील्ड कैन नॉट डू वर्क ऑन अ स्टैटिक चार्ज, सिंपल एज दैट।
सही।
अगर इलेक्ट्रिक फील्ड एग्जिस्ट कर रहा है तब मैग्नेटिक फील्ड जो है ना, अगर हमारे पास वोल्टेज है प्लस माइनस, उसकी वजह से अगर हमारे पास इलेक्ट्रिक फील्ड है, ठीक है, इलेक्ट्रिक फील्ड है, इलेक्ट्रिक फोर्स है, ओनली देन इलेक्ट्रिक फील्ड क्या करेगा, वेलोसिटी प्रोड्यूस करेगा इस डायरेक्शन में। वेलोसिटी है तब मैग्नेटिक फोर्स एग्जिस्ट करेगा। और इंटरेस्टिंगली वो मैग्नेटिक फील्ड वो फोर्स मैक्सिमम होगा जब, देखो फोर्स मैक्सिमम होगा क्यू ई वी बी साइन थीटा, theta equals to 90 degree. This implies that the magnetic force will be maximum. Okay, अब थीटा किस चीज का थीटा है 90 डिग्री, ये किस चीज का थीटा है,
वी और बी के
हाँ
दरमियान एंगल।
हाँ, वी और बी की,
वेलोसिटी
वी
एंड
और
मैग्नेटिक फील्ड।
हाँ एग्जैक्टली अगर एफ इलेक्ट्रिक हमारे पास एक्स डायरेक्शन में, तो वेलोसिटी हमेशा किस डायरेक्शन में होगी, माइनस एक्स डायरेक्शन में होगी, सिंपल इज दैट। सो इलेक्ट्रिक फील्ड और मैग्नेटिक फील्ड के फोर्सेस का परपेंडिकुलर होना जरूरी नहीं है, ठीक है। अगर परपेंडिकुलर है, अगर वेलोसिटी और मैग्नेटिक फील्ड आपस में, वेलोसिटी तो इलेक्ट्रिक फील्ड की वजह से आ रही है, अगर वेलोसिटी और मैग्नेटिक फील्ड परपेंडिकुलर है तो मैक्सिमम फोर्स आएगा। अगर परपेंडिकुलर नहीं है तो मैक्सिमम फोर्स नहीं होगा, कम हो जाएगा, फोर्स कम हो जाएगा, ठीक है। परपेंडिकुलर कंडीशन सिर्फ मैक्सिमम फोर्स के लिए है। अगर परपेंडिकुलर नहीं है, कोई और एंगल है 30 40 50 डिग्रीज है, तो फोर्स अकॉर्डिंगली रिड्यूस हो जानी है। बट रिमेंबर, फोर्स फोर्स ने कब एग्जिस्ट करेगा, जब इलेक्ट्रिक फील्ड होगा। अगर इलेक्ट्रिक फील्ड नहीं है, देयर इज नो फोर्स, राइट। अगर इलेक्ट्रिक फील्ड नहीं है, देयर इज नो फोर्स, ओके। It also means in the absence of electric field, magnetic fields cannot do work on static charges. या आप ये से भी कह सकते हैं कि मैग्नेटिक फील्ड तो चार्ज को एक्सेलरेट ही नहीं कर सकता, ठीक है। मैग्नेटिक फील्ड स्टैटिक चार्जेस को एक्सेलरेट कर ही नहीं सकता, ठीक है। या स्टैटिक चार्जेस में वेलोसिटी ला ही नहीं सकता, तो इसका मतलब वेलोसिटी जीरो है, फोर्स जीरो है, एक्सेलरेशन है ही नहीं, F equals to ma, right? So it was a very good question, really, and but the question the answer was in a little different way. It's not precisely what you have asked, but the answer is little different in that context. But I hope you have the concept now.
Okay.
So the magnetic flux density B, it's just like the electric flux density we previously discussed. The electric flux density was equal to epsilon E. Okay, this time we have the magnetic flux density, which equals to mu magnetic field intensity. Okay, and this epsilon is epsilon naught, epsilon r. Similarly, mu is mu naught, mu r. So here is this concept. Okay. So magnetic flux density is going to give you magnetic lines of forces per unit area. Okay. This magnetic flux density B term is also going to define the magnetic induction. Okay. Its unit is Webers. Its unit is Tesla. Tesla is a big unit, big unit. It's Webers per meter square or kg per second per ampere. 1 Tesla is a big unit, as the field intensity generating 1 Newton of force per ampere of current per meter of the conductor. Okay, so 1 Tesla is going to cause 1 Newton of force per ampere. Okay, per ampere, and look, if अगर मैं इसको एक एग्जांपल के तौर पे ले लूँ तो कैसे? अच्छा, अगर हम somehow ये देखिए, ये ओरिएंटेशंस है ना, एफ की, वी की और एफ की, वी की, और ये सारी ओरिएंटेशंस अगर हम कंसिडर करें, राइट, तो हम ये देखते हैं कि अगर somehow अगर हम एक कंडक्टर से 1 एम्पेयर करंट ड्रॉ करें, 1 एम्पेयर करंट फ्लो करें, और उसका क्रॉस सेक्शन इसकी लेंथ 1 मीटर है, ओके, और क्रॉस सेक्शन इसका 1 यूनिट क्रॉस सेक्शनल एरिया है, तो इसने जनरेट करना है 1 न्यूटन ऑफ फोर्स. ओके, 1 न्यूटन ऑफ फोर्स से अगर मैं कहूँ कि मेरा मास है से 80 kg, राइट, ओके, I know G is 9.8 meter per second square, right? So newtons कितने आने? mg, which is 80 into 9.8, which is nearly like 800 newtons. This is the force the earth is applying on me downward. Okay, my weight also. Okay, so see, this is only 1 Newton, 1 Newton of force, 1 Newton of force per ampere of current per meter of the conductor is 1 Tesla. Okay, it's just 1 Tesla. Go through these few links. This one is for surely active. बाकी आप चेक करें एक्टिव है आज के दिन या नहीं है, बिकॉज दे आर फ्रॉम द फ्री साइट, समटाइम्स इनएक्टिव हो जाते हैं, दे डू नॉट पे फॉर देयर डोमेन. बी गिवन. जी जी
सर, ये पीछे कितना सिलेबस रह गया सर?
बस थोड़ा सा ही है, मैग्नेटिज्म है, थोड़ा सा है
सर. यही स्लाइड है, यही स्लाइड है?
नहीं, एक और भी है, एक और भी है.
अच्छा सर, ठीक है,
ठीक है. अच्छा, so Earth's magnetic field is half a Gauss. Okay, as I said, Tesla is a big unit. 1 Tesla has 10,000 Gausses. 1 Tesla is 10,000 Gauss. Okay, so smaller unit is Gauss, or you say 1 Gauss is 10 to power minus 4 Tesla. Okay, 10 to power minus 4 Tesla. So Earth का जो magnetic field है वो half a Gauss है. It's too small. Okay, Earth's magnetic field is too small, like 5 into 10 to power minus 5 Teslas. Okay, 1 Tesla is nearly 10,000. So 1 Tesla is 10,000 times more than the Earth's magnetic field. A typical hair dryer machine has a magnetic field which is producing a magnetic field because of those currents flowing through the circuit to 20 times of the Earth's magnetic field. A color TV, older TV, has 2% Earth's magnetic field. Smaller bar magnet will produce like 10 to power minus 2 Teslas. MRI body scanner, MRI machine, which is used for this MRI magnetic resonance imaging is 2 Tesla. This is nearly equals to 20,000 times the Earth magnetic field. Okay. So see, these are the few numbers which will give you an idea about the magnetic field, how strong different material have the magnetic field. Any question here?
Yeah, no sir. Sir, बस करे ना.
बस करूं? आज हमारा सेशन
Yes sir.
वैसे चले, ओके, इट्स ओके। अच्छा,